Hello, welcome. In this video we are going to discuss the notion of adjacency matrix. Adjacency matrix can be defined for undirected graphs, directed graphs and weighted graphs as well. Okay, first we come to the definition. An adjacency matrix is a matrix which describes a graph by representing which vertices are adjacent to which other vertices. If G is a graph of order n, then its adjacency matrix is a square matrix of order n, where each row and column represents to a vertex of G. The element aij of each matrix specifies the number of edges from the vertex I to the vertex j. An adjacency matrix of a simple graph or a non-digraph or a loop digraph. A loop digraph is a logical matrix. What's a logical matrix? It's a matrix which contains either 0 or 1. An adjacency matrix for an undirected graph is symmetrical about the main diagonal. And this is because if the vertex I is adjacent to the vertex j, then the vertex j is adjacent to the vertex I. An adjacency matrix for a weighted graph or a network contains weights or edges as entries in the matrix. Examples we have the following examples. First we consider a simple graph, and this graph contains 4 vertices and 4 edges, 4 vertices and 4 edges, and the vertices are labeled here. For drawing neatly the with the adjacency matrix, labeling the vertices is an important matter. So see the labels v1, v2, v2, v3 and v4 are the labels given, and we have the edges connecting v4 and v3, then v1 and v3, v1 and v2, then v2 and v3. And using these connections, using these edges, we can and the vertices, linking the edges, we can write the adjacency matrix. See, in the adjacency matrix, how many vertices will be there? How many rows will be there? 4 rows will be there. First row will represent the first vertex, second row will represent the second vertex, and third row representing the third vertex, and the fourth row representing the fourth vertex. In the same way, the columns also, number of columns also will be 4. Each column will represent a vertex in the graph. We can take the vertices in the same order. Then v1 has the first column, v2 has the second, the v3 has the third column, and v4 has the fourth column. Now you can see how the entries are made in the matrix, how the values are given in the matrix. See the first row, we consider the first row and first column. First row in the first column in the first row, okay, and that's a 0. You can see here it's 0 given because the first vertex v1 here, first row stands for the first vertex, and again first column stands for the first vertex. So, and in the graph there is no loop connecting v1 to v1, so 0 is the number given. And then v1, from v1 to v2, see here there is an edge in the graph. From v1 to v2 there is an edge in the graph, so 1 can be, number of such edges is 1, so that number is given as the entry. In the same way, you can the same edge can be taken as an edge from v2 to v1. Therefore, the 2-1 entry, that is the second row first column entry, will also be same 1. Okay, and in this way you can another example, in the first row the third entry can be determined using or considering the number of edges, by considering the number of edges that connects v1 to v3, v1 to the vertex v3. Here v1 to v3 number of edges connecting is only 1, so you can write there 1. Then the next entry from v1 to v4, See, in the graph v1 to v4 there is no edge connecting the two vertices, so you have to fill 0 there. And in the same way, each row, elements in each row can be determined and entered. Then coming to the example of a multigraph. Multigraph, what is a multigraph? Multigraph must contain some multiple edges. A multigraph must contain some multiple edges. You can see in this graph how many vertices are there: v1, v2, v3, v4, v5 and v6. There are 6 vertices, and also edges are present, but you come to this edge, you can see more than one edge connecting the vertex v2 and v3. So they are called, these edges are called multiple edges. Thus we have multiple edge at one position, and that is between v2 and v3. And at one more position we have, at one more place we have multiple edge, that is between v5 and v6. See here, v5 and v6, there are 3 edges actually. You can count the number of edges, because that number is very important when we prepare the adjacency matrix. Now we can come to the preparation of adjacency matrix. See, in the adjacency matrix, you can how many rows you can choose? You can choose see 6 rows, because each row must represent a vertex, and so for v1, first row represents v1, then second row v2, and third row v3, etc. You have to choose for 6 rows for representing the last 6th row will represent the last vertex. Similarly, you can choose columns to represent one by one the vertices, and then to find the entries in the matrix. Thus we have now a 6 by 6 matrix, square matrix. In this matrix, entries must be made, and these entries can be made using the or counting the number of edges connecting the vertex vi to vj. So in order to fill the first position, 1 position, you have to consider the vertex v1 and then to v1. v1 connecting, how many edges are there connecting v1 to v1? And there is 0. Then there is no edge, so 0 is the entry. Then v1 to v2, how many edges are there? There is only 1, so 1 is given. And but from v1 to all other remaining vertices, there is no edge from starting from v1 and going to other remaining vertices excluding v2. So and yeah, this tells us that we have to fill 0 in the remaining places. So from v1 to v1 to v3 you have to put 0, from v1 to v4 you have to write 0, v1 to v5 0, and v1 to v6 0. After that you can start entering values in the second row, but when you come to the second row you have to consider the second vertex. So there is a change in the vertex. The fixed vertex now is changed, or our attention has now changed to the second vertex v2, and from v2 you have to consider the remaining vertices. So v2 to v1 there is 1 edge, so you can put 1, and from v2 to v2 itself there is no there is no loop present in the graph connecting v2 and v2 to v2, so we fill 0 at the 2 position. Then from v2 to v3, there are 2 edges, multiple edges, so the number 2 is given there. And from v2 to v4 there is only 1 edge, so the entry is 1, and v2 to v5 there is no edge, so 0 can be given. And from v2 to v6 also the same is the situation, 0 is the entry, 0 edges, so 0 is the entry. In this way you can expand the matrix. You can enter or find the values in each cell in the matrix, and you can enter those values and finally finish that matrix. Okay, now coming to another example, the diagraph. In the case of diagraph, but it's the property of a diagraph. In a diagraph you can see that edges are directed. Some direction will be associated with each edge present in the graph. That's why this name diagraph is given to that graph. And these directions can be, but in between two vertices, some edges can be present in both directions. Okay, in between some vertices, as you can see here, here V1 and V4. See, V1 and V4, these two vertices. Between these two vertices, you have the edges connecting, direct edges connecting in both directions. Now you can be following the same procedure. You can complete the matrix. See, this in this matrix, how many vertices will be there? 1 2 3 and 4. There are four rows and 4 columns will be there, and you can fill up the entries in the matrix. And now in the case of loop graph, graphs having loops, the same way you can fill up the same procedure can be used to fill up the entries, and you can make the matrix. Okay, then coming to loop multigraph. Okay, then there are some examples in which both the loop and multiple edges are also present. So loop multigraphs will be there. Okay, can be considered for making that matrix, and that's also in a similar way you can make that matrix. Then a loop diagraph. Okay, loop multigraph and then loop diagraph. Loop diagraph is a graph in which this some loops are present the same time edges are directed. In that case also you can prepare the adjacency matrix in a similar way. Then another example is very important. It is network. In the network, that some directions may be there, maybe some maybe directions absent. Okay, but another important fact about the network is that the edges may be given weights. So in such cases, if the edges are given weights, you have to fill up that weight as the entry in the matrix. See here in the matrix, in the graph we have edge connecting, a direct edge from V1 to V2, having the weight 1.2. So in the first row, V1 stands for the first row. So in the first row, V2 decides the column. So in the first row, the second column, you have to fill 1.2. That is the weight of that the associated edge. So in this way you have to find out the position of the weights in the matrix, and you have to fill up that matrix. That will be the matrix associated with the network graph. Okay, and then you can for further to know further about this kind of adjacency matrix, you have the following. You can use the following sources. Okay, thank you.